At the dawn of the 20th century, physics faced a crisis. The magnificent edifice of classical physics built upon the unshakable foundations laid by Newton and Maxwell was showing cracks. The problem lay not in explaining the grand cosmos, but in understanding the smallest constituents of matter and energy. Classical physics with its elegant equations could predict the motion of planets and the behavior of light with remarkable accuracy. Yet when applied to the microscopic world, it faltered. One glaring anomaly was the ultraviolet catastrophe, a prediction that hot objects should emit infinite energy in the ultraviolet part of the spectrum. This was clearly absurd. The classical picture of the atom, with electrons orbiting a nucleus like planets around the sun, also faced insurmountable problems. According to classical electromagnetism, accelerating charges should radiate energy. This meant that orbiting electrons should continuously lose energy, spiraling into the nucleus and causing the atom to collapse. Clearly, something was amiss. The stage was set for a revolution, a radical departure from the established order. The world of physics was about to be turned upside down. In 1900, Max Planck, a German physicist, proposed a radical solution to the ultraviolet catastrophe. He suggested that energy, instead of being continuous, was emitted and absorbed in discrete packets or quanta. This was a revolutionary idea that challenged the very foundations of classical physics. Imagine a staircase. You can only stand on one step at a time, not in between. Planck's hypothesis suggested that energy behaved similarly, existing in quantized levels, like steps on a staircase. The energy of each quantum was proportional to its frequency, a relationship elegantly captured in his famous equation, E equals hf. This simple equation with Planck's constant h held the key to unlocking the mysteries of the quantum world. It was a revolutionary idea, a paradigm shift that would forever change our understanding of the universe. Planck himself was hesitant about the implications of his own hypothesis. He initially saw it as a mathematical trick, a way to make the equations work. Little did he know that he had stumbled upon a profound truth about the nature of reality. 5 years after Planck's groundbreaking work, a young Albert Einstein would take the quantum hypothesis to its next logical step. Einstein, known for his revolutionary ideas, applied Planck's concept of quantized energy to explain a phenomenon known as the photoelectric effect. The photoelectric effect, discovered by Heinrich Hertz in 1887, involved the emission of electrons from a metal surface when light shines upon it. Classical physics predicted that the energy of the emitted electrons should depend on the intensity of the light. However, experiments showed something astonishing. The energy of the electrons depended not on the intensity, but on the frequency of the light. This was a complete mystery from the classical perspective. Einstein, however, had the answer. He proposed that light itself was quantized, consisting of discrete packets of energy called photons. The energy of each photon was determined by its frequency, just like Planck's quanta. When a photon strikes the metal, it transfers its energy to an electron, giving it enough energy to escape the metal's grip. Einstein's explanation of the photoelectric effect was a triumph for the quantum hypothesis. It showed that light, long considered a wave, could also behave as a particle. The wave-particle duality of light was born, a concept that would become central to quantum mechanics. In 1913, Niels Bohr, a Danish physicist, took the quantum revolution to the heart of matter, the atom. Bohr's model of the atom combined classical physics with quantum concepts to explain the stability of atoms and the discrete nature of atomic spectra. Bohr proposed that electrons in an atom could only occupy specific quantized energy levels, much like Planck's energy steps. These energy levels were determined by the angular momentum of the electron, which was quantized in units of Planck's constant. When an electron transitioned from a higher energy level to a lower one, it emitted a photon with energy equal to the difference between the two levels. This explained the discrete lines observed in atomic spectra, a phenomenon that had puzzled physicists for decades. Bohr's model, though a major breakthrough, was still a semi-classical model. It incorporated quantum concepts but relied on classical physics to describe the electron's motion within each energy level. A complete quantum theory of the atom was still years away. The early 20th century witnessed a flurry of activity in the field of quantum physics. Physicists grappled with the strange and counterintuitive nature of the quantum world. One of the most perplexing aspects was the wave-particle duality of matter. If light, previously thought of as a wave, could also behave as a particle, could particles like electrons also exhibit wave-like properties? Louis de Broglie, a French physicist, proposed just that in his 1924 doctoral thesis. De Broglie hypothesized that all matter, not just light, had a wave-like nature. He proposed that the wavelength of a particle was inversely proportional to its momentum, a relationship known as the de Broglie wavelength. This radical idea was experimentally confirmed a few years later, demonstrating the wave-particle duality of electrons. The wave-particle duality challenged the very foundations of our understanding of reality. How could something be both a wave, spread out over space, and a particle, localized at a point? This question would lie at the heart of the debate about the interpretation of quantum mechanics.